it's a little bit difficult to just show everything. So what I try to show here now is just a general introduction to the program, okay? I will show you something like I didn't show before on thin film, because we will not go through a tutorial on thin film, so you will just see what it does. And then we will just go through an example in which we deal with size strain, so crystallized size, microstrain. And then in the workshop, I will concentrate instead on, we will do something concerning, okay, starting from an image, and we will do the Montmorillonite analysis I showed yesterday on the quantitative analysis lecture. So starting from the image, integrating it, and so in that way we will see a little bit of structure in which we need to put this octahedra and refine their position and occupancy, and also we can go through how we deal with texture on it. Okay, so let's go further. So we see what are the main goals of the program, actually MAUD, how it works, and what is good for mainly. So it's not a classical Rietveld program, MAUD. It also is different from how it was conceived and how it works. Okay, so actually the main goal of MAUD when I started was to do material analysis. So it was not to do structural analysis only, but just the kind of analysis the material science do mostly, and people, okay, and field around. So as you see, like Gilberto was showing, there are a lot of different fields interacting with that. So some specific objectives of the program are what interests mostly material analysis or material scientists is quantitative phase analysis, okay, and characterizing the microstructure, so crystallized size, microstrain, but also for some of them it's important to go more deep into texture, residual stress, and then working on thin film. Thin film is a big field in material science. Okay, and what kind of method it uses? So it's based on the Rietveld, but not only. So normally what we use is multi-pattern analysis. So one analysis can deal with one pattern or several patterns. Not only, so we join several kind of analysis from neutron, electron, or diffraction, and you have several Rietveld programs who do that, but we are also combining different techniques. So for example, reflectivity with XRD, so that is quite good for thin film, and actually we are working a lot also now on XRF and other, okay? And as much as possible, MAUD tried to deal with physical parameters. So we are not interested in unphysical value just to fit our data. We are interested to get the physical parameter that are good for our material analysis. So about the functionality, so there is a Rietveld pattern fitting, okay, the core, so that actually can deal with different methods. So we have the structural analysis part, so the crystallographic part, but also size strain, so crystallized size and strain method, okay. MAUD doesn't do one method. MAUD was constructed from the beginning with a plug-in structure, mainly for me, because for me it's more easy than to put different model. I like to test, when I do an analysis, to use different model, because actually there is not, in every field there is not one model. You learn from this school, there is not one model that fit every sample. So sometimes your sample or your structure you can characterize better by super flip, sometimes by direct method, sometimes you have to. So the idea is that you want also to test different methods and see which one is more suitable for the kind of analysis you are doing in that model. And so I said mainly for me, but also, well, there are actually very few people who have wrote a plugin for MAUD to extend the functionality. Okay, so texture is a big one in it. I would say that I worked more on texture in the last 15 years than on anything else. Residual stresses, thin film, okay, we deal. And then actually, so from the, let's say from the more crystallographic part, actually MAUD can do also indexing. Yeah, it's not maybe, and so peak location, peak fitting. Yeah, but not only using, so you can do indexing also by full pattern indexing or similar technique. Yeah. Well, labile fit you can extract actually electron map. This is actually not updated too much. So we have different technique, reflectivity. We deal also with the ADXS. That one is ready, but and I am actually had to take out some bug from the XRF part that is in, and we work with X-ray, neutron, and electron. And every of these parts, as I said, has different algorithm, different method, and can be extended very easily. For example, actually, when we do the pattern fitting, MAUD you can do using a simple least square marker method, but you can do evolutionary, you can use evolutionary algorithm, simulated annealing, simplex. Yeah, that someone bring back the simplex. I was using it more than 20 years ago. Yeah, genetic or well metadynamics. Actually, the one I like more, I forgot to put in. There is a hybrid method. Someone described it is a genetic algorithm combined with the marker least square, and is very efficient. And so, for example, in the side train, then you can use something like a simple method, side train, like the one developed by people at Delft. The model you find in the Young book, okay, the simplified model, or you can plug in, so you can use the proper anisotropic description. You can use directly size and microstrain distribution, okay? So you can use MAUD without any absorption on the peak shape. Well, I would say you don't do any absorption on the peak shape, but you do on the distribution, because you choose, I have a log normal distribution, or I have a another kind. So simply the absorption go on another level. But is a little bit slower, but when you have complex kind of share or bimodal distribution, then you really go fitting very well. Okay, and planar faulting, yeah, here, or the single layer, for example. Texture, yeah, the classical Microstructure, Harmonic, VINF, eVINF, these are not based on function, but discretizing the ODF, or standard function has. And actually also the exponential harmonic in addition. So we deal with residual stress. So actually residual stress, we have the geometric mean, void, Royce, Hill, or simple triaxial stress without texture. So we couple texture and residual stress, or the, this is the weighted strain ODF, the method of Pauper-Balzar derived from the Wang method. And yeah, or there were a couple of people developing other for this, like Merkel, for example, you can download. He developed a method that can be put as a plugin in MAUD. So he has a web page that explains how to work with it for high pressure measurement. So a method to get the the modeling for high pressure experiment. Okay, yeah, this is the interface of MAUD. MAUD is that where you have a plotting window, okay? You have a panel in which you put all the phases you have in your sample, okay? And then you put also data set. Each data set is one experiment in which you put all the data file belonging to a single instrument, okay? So you can then put several instruments on it. So if you have a neutron instrument and a X-ray instrument, you have two data sets and you put the data on it. You choose you add a new data set every time in your instrument. You have a changing setup in which, for example, the instrumental broadening is changing, okay, or something else. So actually, here is the windows where you see the plotting, okay, the result of the fitting, okay. And here, for example, you have a simplified file where you see all the parameter and you can change live the parameter. Yeah, or you see if you are refining or they are bound to another parameter or whatever. And some output during the refinement goes over there. And the small toolbar, you change the number of iterations during the iteration or you stop whatever you are. And another one, toolbar on top to assess quickly some of the more used features. Okay? Now, if you just work just quickly, well, this can be done, we will see better directly on the program. So you can load the data file, okay? And the number of data, okay, what we support in MAUD, well, this is one question that I got several times, maybe because I didn't put clearly the information, okay? MAUD recognizes data format based on the extension, okay? So simply, MAUD does not read what is inside, so it just check the extension. So if it has a certain extension, he assumes that the format inside is of a certain type. Otherwise, it failed to load it, okay? So if you mix the extension, will not load your data. So there are several, yeah, there are even a couple of more now, every time I add. So 99% of these are text format. I don't like to deal with the binary format because it takes too much time to implement the loading. So I prefer text format, and practically nearly every instrument has an export in text format that is suitable for MAUD, okay? So you see, if you have a format and has the wrong extension, you just edit the extension, change it, and load in MAUD, okay? If you have problem, or sometime I am not able, some factory, for example, change the format or add some more, and maybe MAUD doesn't load anymore. So you just send me, in case, one example, the file, and I can update the format. Okay? Hopefully, I do it. Okay, so normally, how to load data? The preferred way of the material scientist is just to get a CIF file and load it. Otherwise, you have to input by hand, okay? So, and then second, when you load the CIF, check what has loaded, because sometimes it could be that there are several CIF. In some CIF, there could be some error, or sometimes it's just MAUD that do an error and doesn't recognize some of the CIF, okay? So you check especially the space group, if you recognize correctly, space group, set parameter, and atom position, yeah. Okay, for the atom, then if you are going to put your structure in, in MAUD, okay. You put, choose the atom, whatever. Actually, this is old. We now have, not only you can choose the oxidation state, but yeah, in Los Alamos, they asked me to add also the isotope because they deal, on neutron, they are sensible to the isotope also. Okay? So this is the part you deal with the microstructure. So normally we will see this more in detail. And here you choose the distribution. So you can see you can use distribution of crystallized size microstrain to reconstruct the profile. Yeah, this is anisotropic crystallized size and microstrain. You can couple crystallized size microstrain distribution with anisotropic size strain, okay? Reflectivity, if someone is interested. Here is the sample editing window in which you can put, you see as much layer as you like. Yeah, here was a multi-layered sample, okay? Where you see there we are plotting the critical QC is just because people in reflectivity prefer to plot the critical QC, but it's just like plotting the electron density, okay? Along your depth inside the sample. And so you see, well, this was a sequence repeated several times, so you see the changing in the electron density. And actually MAUD can use, so you can, or you don't put any phase, you work just with reflectivity the classical way, or if you put the phases, you couple the XRD with the reflectivity, so MAUD compute the critical QC from the phase content, okay? And so you can do it a little bit more. It's a little bit more complicated. Sometimes it's more easy to start with the problem decoupled, separated, and then join at the end. Okay, yeah, when you want to, in the option, analysis option, you can choose what kind of algorithm you want to use. So actually, for example, in MAUD there is the parameter list in which for each parameter you have the minimum and maximum value. That one doesn't work with the Marquardt, D square. Normally you don't want to limit the Marquardt. Okay, who developed the Marquardt and people working in D square, they said you don't, there is no, let's say, a clear way to put such constraint on a Marquardt least square. What you use the constraint, so the limit, maximum, minimum, is for all the other evolutionary refinement, so simulated annealing, to generate the first, for example, population need the minimum and maximum value. But for the least square, they are ignored. Okay? And okay, plotting, you can choose different, then output. Yeah, we go quickly through this. I prefer to go directly to the program. One feature of MAUD I use most is actually the wizard. If you have, and I advise who is beginner in the field, always try first to use the wizard, okay? So the wizard is simply what I normally do in a refinement, so I try to schedule it in it, and it's simply an automatic way to go. There are two different kinds of automatic refineries, let's say. On the right, there is simply, you choose an analysis, and the program will go in subsequent cycle, each time adding to the refinement some parameter to get what is your goal. So if your goal is the quantitative analysis, we'll do one strategy. If your goal is crystal structure analysis or texture, we'll do another one, okay? On the left panel, instead, you can go a little bit mix the two approach. So the program decide which parameter to refine, which not, but you decide the sequence of the action. Or what you can do, you can select one, and then instead of pressing the go, that go directly into refinement, you press set parameter, and then you go to the list of parameter, and you revise what the program was doing automatically. So that is what I do most. So I use that one, use the wizard, so he set the parameter for me, most of them, and then I just go and change a few because maybe I don't want to refine this, but another one. Keep in mind that these work with most of the analysis, simple analysis and material scientists do, but doesn't fit all what you want to do. Especially if you are working with a difficult analysis, then okay, you do not rely, or at least not completely, on the wizard. It is very good to start with because what you can use is you select, for example, the step there you want to do, you press set parameter, and you go see which parameter the program decided to refine, and so you can learn which parameter you have to refine and which not, okay? So it's a good way to also learn the procedure. Okay, yeah. So another feature is adjusting parameter live. This I borrowed this from people working in reflectivity. They like to change a parameter on the fly and see the result on your data. And so I put into the ritual, yeah, in which, and it's very good if you have to, for example, in this case, you don't have the correct set parameter, and you go it through this one. So you decide the step, you change with the arrow, and you see the peak shifting, and you put where they want. I use that one to normally adjust at the beginning the analysis. You will see how I do it, okay? So, well, when this one I prepared, not obviously yesterday, not even this morning. Actually, automatic refinement was something MAUD, but actually I think there are several, well, for sure Topaz, but I also other can do, let's say, an expert way to go in which you have to care less. Normally, yeah, myself, if I have a simple analysis, or simple or whatever, I do the automatic analysis, okay? If it doesn't go, then I go through a more customized one. But if it goes, I get the result without any effort. Okay, then, okay, you have this live parameter adjustment. Okay, it was having the multi-threading computation, but actually, I actually decreased it, yeah, because MAUD didn't start with the multi-threading in mind, so it's actually conflicting quite a lot. So sometimes there are some conflict, and so I disable this. If you want, there is a way in the preference to enable it, but I advise. So mostly what it does is 99.9% of the cases it goes, but there is sometimes it fails, okay? So, but you don't feel it because you don't get any error. Simply you get a wrong result, and it's due to the conflict for the different trading. So I prefer to disable it. And I'm rewriting some other program to do it in a different way from the beginning. So I will reserve 5 minutes at the end to just show what I'm working on. Okay, so thin film and multi-layer. Has a ritual program, yeah. Yeah, you can use it without defining any profile function, so using the distribution. Is probably the only one you can work directly with the residual stress or residual strain inside. So with the model, okay? He has not only one texture model, but several, because on texture, sometimes you have to work with one model or another. There is no one really working for everything. Okay? Yeah, work with diffraction images, okay? So in MAUD, the way you do, 10 years ago, we were using Fit2D, but actually, we realized that the problem is that we want to calibrate the image during the ritual refinement, and especially when we deal with residual stresses, because residual stresses, like for example in a high pressure, they change they overlays, for example, the images, okay? And Fit2D treat them as a tilt of the detector. We want to separe the tilting error of the detector from the, for example, the residual state, the high pressure or whatever. So we fit actually the center of the image and whatever. And also other problem, you have an image incline, okay? Well, MAUD deal with every image incline in the space, also reflection, transmission, whatever. If your sample is going a little bit up or down, what is happening is, especially when you tilt the sample, okay, the sample is not in the center of rotation, it goes up or down. What is happening is the center of the image is changing, okay? And so you want to deal with that inside the refinement, okay? That's the reason why actually we load the image inside MAUD to divide in pattern, okay? Because we keep the information where that pattern, so the information on the coordinate on the image, and so we can calibrate, refine the calibration. Okay, yeah. Well, so we have micro-absorption correction, planar defect. Oh, yeah, micro-absorption correction is also implemented in brass. Actually, I don't know, brass, I didn't see brass news in the last 1 or 2 years, but maybe, okay. Amorphous modeling, okay, and different algorithm. Yeah, well, okay, that we have already seen. Okay, yeah, these I think we skip. Okay, and we go directly to see. Okay, here it is. So we just see one example with thin film. As I say, we don't want, but just to see how it works. This is an older example, actually, but it's very good to show. So you measure with an Eulerian cradle PSD detector, 120. So this was a 400 nanometer PCT, okay, film, deposit spin coating. Okay, so what we do, so we collect several patterns. It was, well, normally around 1,000 and something pattern. Okay, the problem with this PCT is that we have the subset, then we have a PT layer, and then we have the PTC. And what is happening is that the platinum layer overlap exactly with the PCT. You see, all the peak of platinum are exactly overlapped with one peak of the PCT. That is the feature they want, because they want the lattice of the PCT match perfectly the PT. So you grow a certain texture, okay? But unluckily, then, from the analysis point of view, you have to. So the retrieval is the only way you can separe the two textures. Otherwise, with normal pole figure analysis, okay, where you measure the pole figure, you cannot measure the pole figure for PT, for the platinum separated by the other. So, but inside the retrieval is quite easy. So in this case, we impose sample symmetry, fiber symmetry, because it was by spin coating, so it's much. Oh no, okay. There is one problem. So here you see apply the harmonic method, and you will see that, for example, in this case, the harmonic method doesn't work because the texture is too sharp, okay? So it's one case in which normally you use the harmonic method with smooth texture. If it is sharp, you cannot use it, so you switch to another one, okay? So, oh, I forgot that. Yeah, it's because using the harmonic. So what is happening? If you don't cut the negative part of the harmonic, and you should not allow it to do that, because then your ODF doesn't anymore represent, so the pole figure doesn't anymore represent your ODF. You get some negative point, because with the harmonic, trying to fit the sharpest part of the ODF, the highest part, he creates some negative point on that. The problem with the harmonic is that you cannot use an infinite expansion of L. So you have no possibility to fit correctly sharp texture, okay, even if you can. So yeah, you see some small negative part, well, some big one there that is due to the, so when you look at the harmonic pole figure reconstruction from the OTF you got from the refinement, okay, there is the PT and here is the PTC. The PT has a higher texture, so you see in the center, you go, okay, this is quite high for the harmonic, 66, but you go -5 in certain point. Yeah, because you have the, and this is the PTC, and also for the PTC you have, even if the texture is less sharp, you get a little bit of, but we will see changing model for texture that this is not, the texture is much higher. It's only that the harmonic cannot deal with it. Okay. So then we use the eVinf, okay, that was just an extension of the VINF method to work better with this kind of, VINF was developed more for the pole figure method. This one worked for the Rietveld best, so we have the fitting, okay, the VINF method, eVinf, you don't get any negative point, it's inside the algorithm, okay? And so, and actually we can even use, we don't need to suppose we have a fiber texture, like for the harmonic. For the harmonic was too much even put in the fiber, without the fiber texture. So you see, and so we got, actually the PT film was not perfect, didn't have a really fiber texture, so the people were not happy and they had to re-prepare it to get it correct. So you see some small dot over there that are coming from the substrate. So you see, and then you see now the, for example, on the PCT, the strength of the texture is double. So the harmonic really didn't get it. Yeah, for the PT instead was nearly okay. And also what the good thing with MAUD, as I said, we combine microstructure, crystal structure, and all the features, so we can refine film thickness, okay, like there, and we got nearly right, okay, and also the crystal structure. Okay, that is, we don't need this one. So now we go through how we work, okay, with MAUD. Okay, this we see later. Okay, so actually with MAUD, what you do, you just go to the web page and you download it. Okay, hopefully, I normally, okay, this is actually, I'm not going really on the web. This is the web page of MAUD. There is nearly, normally I update the program nearly one every month. In the last 1 year I didn't, because I was working on a nearly full-time on another project, not dealing with MAUD. So what you do, yeah, you have several things, and you want to go to the download page to download the program. But I will say, check this one. There are, sometimes I just upload some of my presentations so you can see what MAUD do, or just go to the tutorial, okay? There are also now some, well, now, I put them 2 years ago, yeah, and I didn't finish. I will put some more. Okay, oh, see, yeah, it's still working. A YouTube page for MAUD where you have some video. This is probably the best way to start, because you see how directly how I demonstrate MAUD, how to work with some analysis. I will try to expand it. Well, every time I say that and then I don't do. But as soon, well, normally during the summer I have some time, so I will do some more video to get it. But there is also one for dealing with the images, okay, on this one. So what you do, we just go to the download page. Be sure to get the Java on your, so the main problem are, if you have a Linux machine, okay, it works perfectly if you have the correct Java virtual machine. And that is one of the more difficult point, because normally Linux, Ubuntu, they do not come with a Java virtual machine sufficiently good for MAUD, okay? It's not 100% compliance. It's 99.9%, but the little point and doesn't permit MAUD to run. So what you have to do, you have to you have to install the Java virtual machine provided by Oracle now, okay? And to do that, with every Ubuntu version, for example, is getting more and more difficult, okay? Even one step is if you don't manage, so you have to install, so you have to enable non-recommended repository, okay? Then you have to download it, install, and that is not sufficient. You have to go on the command line and specify you want that Java virtual machine is the default. If you are not able to manage that one, you have to disinstall, so the default one even, okay? So that is the problem with Linux, okay? If you get the correct Java running, then you just can use MAUD. On the other, Windows is more easy, and Mac has already it installed, okay? So we just go here. We just need, okay, if you are on Snow Leopard, you can use the 64-bit. Yeah, that. Actually, if you are like, okay, it's the same. If you are on Windows, you get a MAUD zip. You unzip it. Other problem, okay, some people just double-click the MAUD zip. They get by Windows in a directory, and they think they can run the program from there. No, because you are running the MAUD from inside the zip archive, okay? That way, you have to really extract your file and put in a directory. Otherwise, it doesn't work. So actually put that, yeah, on, so here we go. We have a directory we just put over here. Oh, yeah. I tried. Oh, it exists already and is running, maybe. Well, it doesn't matter. I have done that just before the lecture to see it. Oh, or I can just trash, so I can do it. So here it is, what I download, put over here. Okay. Then this is the virtual disk. On Mac, he mounted a virtual disk containing that one. So MAUD, you can put whatever you want. You just only need the program, and okay, on Mac is like this one, and the plugin directory. On the other, you have even, you see a little bit more, you see directly the jar. So on Windows, you start pressing the MAUD.bat, and on Linux, you can use the .sh, okay? Or you can just type the command line. If you edit the MAUD.bat or the MAUD.sh in Linux, you see which command line is used to start the program, and so you can use that one. So we just say we want to run it. Yeah, actually I put a license, so you have to accept. Then create a folder where MAUD extract your preference file, some database. I normally don't put them where in the same directory where I have MAUD, okay? Because then I can cancel the program but keep all my preference, okay? So I can trash the program, install a new one, okay? And specify again my preference folder is the same, and so I keep all my setting, just reset, just with a new version, okay? So let's, we create a folder. We go on the desktop, yeah, new folder. Oh, I have already, so this was the one from before. So let's say I use the same. It doesn't overwrite file if he found over there. So, okay, that you get if your screen is small, like here, okay? So we try to, it's not, okay, MAUD is better if you have a bigger screen. Actually, here we have, oh no, we can select a little bit more. So let's say with this one. Yeah, okay. Yeah, it works. Oh, much better. I didn't see that. So the video is quite well. Okay, so we can. So now we have some. Okay, there are some examples in MAUD that are saved exactly in the directory we create on it. How much time I have actually? 5 minutes. So okay. So I just show how quickly how I work normally. So let's say I have some data. We can use one from the desktop here, MAUD file. So one is this aluminum and tetragonal zirconia, okay? So what you do is just, you have this one. I got the phase, so you can use drag and drop. So I go to phases, and then I can drag and drop zip file, or even, okay, the MAUD database is actually in zip format. So what it is, structure MDB. So I drag over it. So you open, and then I have, you can store the phases you use most in there. Okay, corundum, where it is, here. And then I want to load also the tetragonal zirconia. Yeah, it's just over here, so yeah. So I load both. So, well, I don't need to check if they are correct. Let's see. I just press the computation button over here. It's only, okay, the intensity is very low, okay? And actually, yeah. So this is very low. So then you want to go with changing your parameter live. I just would like to show something. Isotropic here. So if you want to change the, for example, the crystallized size, okay, let's put the step 100, and then we decrease them. And yeah, actually, these appear, this was what? The corundum. Yeah, over here. Well, I actually don't know what is happening on my, oh no, yeah, they turned out. It was something strange with there. Okay, here it is, so let's see. If you change the crystalline size, you see some of the peaks are broadening, okay? These are in angstrom, so. And in this case, for example, we don't have the correct set parameter for this one, is the one I was showing. So first, I want a little bit more intensity just to see if I am correct. So I just go here. On the instrument, I have the overall intensity. So let's say step of 10, and then you change, okay, your intensity. And you can do it for the background. Let's say I go higher with the background, just to see. Now I should see better, okay, what I have. And then I go over here, okay, and my set parameter. So this because I don't have the correct, I load the phase that doesn't have the correct zirconia composition. So let's the step a little bit smaller. And I have to increase it, yeah? Well, a little bit more bigger the step. Yeah, so here, if I move the set parameter A, I'm moving only this peak, and if I change this one, I move this one, right? Yeah, because I choose two peaks in which one depends only on 00L and the other only on HK0, okay? So let's say now is okay when you have the peak under, and what you do is just you go to the wizard. I want to do a quantitative analysis, press go, and that is done, okay? And so you have a quantitative phase analysis here, and you can check crystallized size, microstructure, whatever. Yeah, and okay, we'll see later more. I want to show one thing. What I was occupied last year that I didn't work on MAUD is this program here. Actually, it worked, okay. It worked on Mac with an interface, on Windows without, okay. So what it is, this does, so I load the database, I constructed it, just put in all the CIF coming from the code and from all the CIF I found around my disk, okay? So I have here nearly 100,000 phases. I can scroll through. Yeah, you can see I have all of them, yeah? So why I have this big database, okay? Because then what I want to do is I load a data file, let's see. For example, this one is from the CPD. Was the same, I think, was shown by Jan Madsen yesterday. And then what I want to do is just, okay, I have here, I want to just say, go with the analysis, so find out what phases you have and the quantitative phase analysis. Actually, here, if you go with 100,000 phases, it takes a little bit of time. So you need a multi-core machine. So you run on my desktop on I have 12 core, 24 thread, and it ran, if I use the full database, in less than 20 minutes. But if I am able to restrict the composition, as for example I can do here, like say, okay, I know here we have only calcium, magnesium, if I remember well. Okay, no, first I have to invert, because I did select some. So let's say I have magnesium, calcium, zinc, if I remember, aluminum, oxygen, and fluorine. I can even add some more. Let's say I don't know exactly if there are also this one. I don't put more atom, otherwise I grow too much the number of phases, and I don't run in 1 minute, okay? Yeah, so then I invert, because I just specify I don't want all the other atom, okay? Okay, then you press OK, and then you go, okay, find best matching. Actually, on this one, so it's something that was developed to work automatically, so you don't see too much, you have to, okay, so you select 110 element. Oh yeah, so we have 120, 200,000, so 1,200 phases. He has already, so what he does a ritual fit for each phase in automatic, so not a ritual fit, an automatic analysis for each phase, all through the 1,000. He has already done, then he select the best one, okay? Put in. Then he start again, do for the second one, and put in again, until the last phase he found is lower than a certain threshold. Okay, has finished. Here is the fit. Actually, you get here the phase content, 3 phases. And if I check this one, yeah, I know are the correct phases, so he has identified the phases and done up to the ritual fit. And actually, this work also with nano, whatever, yeah. Well, I am revising the algorithm testing because the ranking is not straightforward, so I have to test with several. And actually, when it fails, it's just because there is not that phase in the database, okay? But in that case, I cannot quantify by the ritual. So, yeah, that is another problem. Okay.
And let's have a few questions. Okay.
For the last program you're showing for the phase identification, Is it something you distribute or?
Okay, yeah, that is a program. So it was developed inside the European project. There is a consortium, so SMEs. So in principle, it belongs to these SMEs, okay? But in the SMEs, there is no one working in diffraction. The only one is in RTD, so has not the right for it. So, and actually the best thing for this one is probably to deal directly with some, so to get an agreement with a company like, I don't know, who distribute the ICSD, because it works better if you have a complete database. For example, the code doesn't provide a complete database, so it's something. Well, what I would like is to distribute it. And it's actually, the core of this one is the next MAUD, so that's...
and since the ICDD is commercial...
yeah, I don't know, yeah, actually, that is... yeah, that's the reason I can only demonstrate up to now, not...
we are going to have a workshop after the coffee break, and I think that anybody who has further questions to Luca Lutterotti can ask that, I think, at this occasion. So let's thank the speaker again.
Okay, there we go.
And,
Okay, we're going to move on to Student Corner. This is a traditional event at Arici where you have the opportunity to take all the speakers to task, and the questions that you wanted to ask but never got around to doing it. This is your chance to do that now. Now, Tamas is actually, because he's not had the opportunity to show some of his software, is going to spend 10 minutes now doing that, and then we'll ask the Friday, Saturday, Sunday, and Monday lecturers to come up to the panel here, and then please have your questions ready. Remember, the Ludovico Prize is still up for grabs.
Thank you, Bill. Well, it's not coming.